I have no information about a generator with the name HTETCO. It is possible that the name is misspelled or refers to a very specific or uncommon type of generator. Let's discuss some common types of generators. Firstly, there are synchronous generators. These generators operate by converting mechanical energy into electrical energy through the principle of electromagnetic induction. They are characterized by having a rotating magnetic field that is synchronized with the electrical frequency of the generated voltage. The key components of a synchronous generator include the stator, which houses the armature winding where the output voltage is produced, and the rotor, which carries the field winding that creates the magnetic field. The rotor is driven by an external mechanical power source such as a steam turbine, gas turbine, or diesel engine, causing the magnetic field to rotate. As the magnetic field sweeps across the stator windings, it induces a voltage in them. The frequency of the generated voltage is directly proportional to the speed of rotation of the rotor and the number of poles in the generator. Synchronous generators are widely used in power plants to generate electricity for the grid because they can maintain a stable voltage and frequency. Secondly, there are synchronous generators. Asynchronous generators, also known as induction generators, are similar in construction to induction motors but are operated in reverse to generate electricity. Unlike synchronous generators, asynchronous generators do not have a fixed relationship between the rotor speed and the frequency of the generated voltage. Instead, they rely on an external source of reactive power to establish the magnetic field in the generator. The stator of an asynchronous generator is connected to the power grid, which provides the necessary reactive power. When the rotor is driven above the synchronous speed, it generates electricity and feeds it back into the grid. Asynchronous generators are commonly used in wind turbines and small-scale hydropower plants because they are relatively simple, robust, and require less maintenance than synchronous generators. Thirdly, there are direct current generators. Direct current generators produce direct current electricity. They operate on the same principle of electromagnetic induction as alternating current generators, but they use a commutator to convert the alternating current voltage generated in the armature winding into direct current voltage. The commutator is a mechanical device that consists of a set of copper segments mounted in the rotor and connected to the armature winding. As the rotor rotates, the commutator segments make contact with stationary brushes, which are connected to the external circuit. The commutator reverses the direction of the current in the armature winding each time it changes direction, resulting in a direct current output. Direct current generators are commonly used in applications where direct current power is required, such as in battery charging, electroplating, and welding. Fourthly, there are permanent magnet generators. Permanent magnet generators use permanent magnets to create the magnetic field, eliminating the need for a field winding and an external power source for excitation. This makes them more efficient and reliable than generators that use electromagnets. Permanent magnet generators are commonly used in small-scale applications, such as wind turbines, micro-hydro plants, and portable generators. They are also used in some electric vehicles and hybrid electric vehicles. The performance characteristics of a generator are crucial for matching it to the load and ensuring stable operation. These characteristics include voltage regulation, frequency regulation, efficiency, and power factor. Voltage regulation refers to the ability of the generator to maintain a constant voltage under varying load conditions. Frequency regulation refers to the ability of the generator to maintain a constant frequency under varying load conditions. Efficiency is the ratio of the electrical power output to the mechanical power input. Power factor is a measure of the phase difference between the voltage and current. Generators are rated in kilowatts or megawatts, which indicates their maximum power output. The selection of a generator depends on the specific application and the power requirements. Factors to consider include the type of fuel available, the size and weight limitations, the noise level, and the cost. Regular maintenance is essential for ensuring the reliable operation of a generator. Maintenance tasks include checking the oil level, cleaning the air filter, inspecting the spark plugs, and testing the battery. Generators should also be inspected regularly for signs of wear or damage. Now let's consider the electrical aspects of generators. Generator voltage depends on the design and intended application. Generators produce alternating current, AC, which is then used directly or converted to direct current, DC, depending on the need. Typical voltage levels for generators range from 120 volts for residential use to thousands of volts for industrial applications and power grids. In North America, common single-phase voltages are 120 volts and 240 volts. Three-phase voltages include 208 volts, 240 volts, 480 volts, and 600 volts. These voltages are standardized to ensure compatibility with electrical devices and equipment. Generator amperage, or current, is determined by the generator's power rating and voltage. Amperage is calculated using the formula power equals voltage times current. For example, a 5 kilowatt generator operating at 120 volts can supply approximately 41.7 amps. Understanding the amperage capacity is crucial for selecting the appropriate sized generator and ensuring that it can handle the intended load. Generator resistance and impedance are important factors in determining the generator's performance and efficiency. Resistance is the opposition to the flow of current in the generator's windings. Impedance is the total opposition to current flow, including both resistance and reactance. Reactance is caused by the inductance and capacitance of the generator's windings. Lower resistance and impedance result in higher efficiency and better voltage regulation. Generator wiring involves connecting the generator to the electrical system. This requires careful consideration of wire size, insulation, and grounding. The National Electrical Code, NEC, provides detailed guidelines for generator wiring to ensure safety and compliance. Proper wiring is essential to prevent electrical hazards such as shocks, fires, and equipment damage. Grounding is a critical safety measure that provides a path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. Generators should be grounded according to NEC requirements. Overcurrent protection is necessary to protect the generator from damage due to excessive current. Circuit breakers and fuses are used to interrupt the current flow in the event of an overload or short circuit. The size and type of overcurrent protection device should be selected based on the generator's capacity and the wiring system. Voltage regulation is the ability of the generator to maintain a constant voltage under varying load conditions. Automatic voltage regulators, AVRs, are used to control the generator's output voltage. AVR adjusts the excitation current to compensate for changes in load to maintain a stable voltage. Frequency regulation is the ability of the generator to maintain a constant frequency under varying load conditions. Governors are used to control the speed of the generator's engine. Governors adjust the fuel supply to compensate for changes in load and maintain a stable frequency. Generator efficiency is the ratio of the electrical power output to the mechanical power input. Higher efficiency results in low fuel consumption and reduced operating costs. Generator efficiency is affected by factors such as the generator's design, load, and operating conditions. Now let's talk about generator applications. Emergency power is one of the most common applications for generators. Generators provide backup power during power outages, ensuring that critical systems and equipment can continue to operate. Emergency generators are used in hospitals, data centers, and other facilities where power interruptions can have serious consequences. Portable power is another important application for generators. Portable generators are used to provide power in remote locations where there is no access to the grid. They are commonly used for camping, construction sites, and outdoor events. Prime power generators are used as the primary source of power in areas where there is no access to the grid or where the grid is unreliable. Prime power generators are used in remote communities, mining operations, and other off-grid locations. Standby power generators are used to provide backup power in case of a power outage. Standby generators are typically installed in homes and businesses to provide power for essential appliances and equipment. Cogeneration, also known as combined heat and power, is the simultaneous production of electricity and heat from a single fuel source. Cogeneration systems use generators to produce electricity and recover the waste heat for heating, cooling, or other purposes. Cogeneration can improve energy efficiency and reduce greenhouse gas emissions. Renewable energy integration is the use of generators to integrate renewable energy sources such as solar and wind into the grid. Generators can provide backup power when renewable energy sources are not available and can help to stabilize the grid. Generators play a crucial role in ensuring a reliable and resilient power supply. They are used in a wide range of applications, from emergency power to prime power to renewable energy integration. Understanding the different types of generators, their performance characteristics, and their applications is essential for selecting the right generator for a particular need. Proper installation, operation, and maintenance are crucial for ensuring the safe and reliable operation of generators. I recommend consulting with a qualified electrician or engineer to determine the best generator for your specific needs and to ensure that it is installed and operated safely and in accordance with all applicable codes and regulations.